Hello and welcome to the final meeting of this year's Turba online discussion group on the history of alchemy, broadly defined. So my guest tonight is Vojtech Kase from the University of West Bohemia in Czechia. Unfortunately, Petr Pavlas from the Czech Academy of Sciences, who is co-listed as speaker in the poster and abstract, cannot participate due to health problems. So I will introduce Vojtech now. Vojtech Kase is assistant professor at the Department of Philosophy in University of West Bohemia in the beautiful town of Pilsen or Pilsen. There he directs the Computing Culture and Society Lab, CCS Lab, and teaches digital humanities. His research examines the long-term dynamics of human cultures and societies, particularly within the history of Western thought from antiquity to the early modern period. He combines the insights from cognitive and evolutionary sciences with computational methods, including quantitative text analysis, network modeling, and large-scale cultural data analysis. In respect to the project Tom, which was last session and this session is also about, Wojtek was the team leader of the computational historical group. Now, before I proceed, as usual, please keep your video on if you can and the sound off. And I will be taking questions at the end, either if you post them in the chat or you raise your hand virtually. The meeting is broadcast online via the Czech YouTube channel, and you can ask questions there as well. As always, I would like to thank the Society of the History of Alchemy and Chemistry, which is providing its Zoom account and YouTube for our use. I will now give the virtual floor to Wojtek, and Wojtek will be speaking on Inside the Latin Semantic Space, tracing the shifting meanings of words from antiquity to early modern science and alchemy. So Wojtek, at your leisure, please, if you would like to share your screen.
Yeah. Good evening, everyone. Thank you, Joe, for inviting me and for this introduction. I will cover in my talk something what we worked on for the last couple of years. Maybe I will also show you some stuff we are working on right now, so something for the future, hopefully. And as Joe mentioned, I actually worked at the Department of Philosophy, and my background is in the humanities. So even while I will introduce some maybe computationally possibly heavy stuff, I still hope that I will manage to explain it in an understandable way to an ordinary humanities audience. So desktop 2, screen my share. So do you see my presentation now?
Yes,
Perfect.
it's all good.
So the presentation will be mainly about introducing one specific tool. The tool is called iBeams. It's available online on our server, and we also, for maintenance, we also deploy it somewhere else. You can try it on your own already now or later after the presentation. And I would also encourage you to look at the paper which is accompanying this this online tool, where we explain all the technicalities and all the design decision behind this paper in more detail. At some point in the presentation, I hope that I will be able to give you some hands-on showcase of how it works. But first of all, I will have to give you some background, and I hope that using that, you will be able to understand why this has some potential for the history of alchemy in a broader sense, as Joe mentioned. So The context, the methodological context of what I will present here is within the field of computational history, computational humanities, and the methods can be broadly described as computational text analysis. That's at least how it's called usually in the context of social sciences. If we would speak to people in computer science, we would probably talk about text mining or natural language processing or historical language processing. It's also closely related to what is happening in the fields of computational linguistics and stilometry. And in the context of the humanities, perhaps the most famous phrase how to describe this kind of method is the phrase of so-called distant reading, which was actually developed quite independently of a lot of this stuff, which I will introduce here. But for a humanities audience, it's actually the best term how to explain what we are trying to do here, that we are doing some sort of close reading in contrast to what we do usually in terms of so-called close reading. I will elaborate it shortly. The first assumption of this is that we treat texts, or basically any source of linguistic data, as computational tractable data. What that means, computational tractable, that means that it is something what can be processed by computers. So at the end, somewhere in behind, there are just some bits of information, 0 and 1s. And in this 0 and 1s, there is somehow encoded what we, the language we speak or write in our texts. As the most basic thing we can do once we have textual data, once we have text in the form of computational tractable data, is that we can very easily count stuff like word frequencies, which can be used as indicators of importance of words, right? This is very intuitive way how we can nowadays easily investigate any text. We can just count the words which are appearing in it and listing just the most frequent words. We already get some impression what the whole text is about. If we list 100 most frequent words from a text, we get a very clear picture of the content of the text, of what the text covers. In many places, you can encounter this so-called word clouds, which basically do just that they visualize the most frequent words from a document. But still, this is I would say very basic stuff. If we move on, we can also analyze word probabilities distribution. That means that we analyze like corpus of certain documents, and we look at which words appear in what documents, and on that basis we can make some guesses about some topical distribution over this text. This is again a very famous thing and very common actually in the humanities context and in the context of digital humanities, this so-called topic modelings. We can also adopt different methods for analyzing word co-occurrences. So that means, like, again, it has a very rich history in our fields. For decades, or maybe even for centuries, humanities researchers know about the possibility to extract concordances. That means the actual context in which a word appears within a corpus, and then to look at what are the most common co-occurrates of a specific term, like that we know that anima is appearing together with some other terms in some historical Latin texts, right? That was already one of the biggest first project in the context of the digital humanities. The digitization of work of Thomas Aquinas actually already implemented this functionality from the 60s, 70s on. And but this is still something what is very easy to understand and grasp, I think. But then you can hear a lot about so-called word vector representations or word embeddings, which is a family of methods which allow us to scrutinize deeper semantic patterns and even to grasp and analyze semantic change. And this is a big family of methods and algorithms. We will cover only a small part of that, the one which is relevant for the thing we use in our tool. But I think we have to spend some time on explaining what it actually is, because my experience is that there's a lot of misunderstanding of how these algorithms works, because people sometimes tend to confuse them with word concurrence analysis. But it is something different. I would say that it somehow moves the analysis on yet another level when we start to speak about word vector representations or word embeddings. But I think it will be useful to explain some very basic stuff at first. So here, just one slide on distant reading. Maybe we can skip this one. If you don't know this term, you can check this publication, which made it basically famous. But it's even a couple of years older than this publication from 2013, this term. And it is now a sort of a buzzword within digital humanities community. So another important distinction we have to make, or sort of a clarification, is what we are speaking about when we speak about computational text analysis, and at what level we actually operate here. When we speak about digital humanities, digital approaches in the humanities, digital scholarship in the humanities, we again have to identify that this is something what consists of different phases, and which should not be treated as one, I would say. One thing is digitize something, and this is something what is extremely valuable for all of us. If something is digitized, that we can access it online somewhere, but it is still something different than to have something what is also useful as computational tractable textual data, because if it's only digitized, many books actually are digitized but only have a form of images, which still makes them useless for stuff I want to introduce here. Any digitized text also has to go through optical character recognition to obtain a sort of machine readable text. And this is the topic Joe covered last week, right? Like that we have digitized, we have to digitize alchemical prints, then we have to adopt some sort of optical character recognition, which is a complex thing. Again, this single step could be elaborated into a very complex thing here. But this is not the subject of my talk. That was explained last week. What are the challenges you can encounter in this process, especially when working with historical prints and historical languages. But at the end of the pipeline, you hope to get not only a text you can search for specific patterns, specific words, but a machine readable text. And a machine readable text is a sort of a terminus technicus, that it is a text which is running from the opening sentence to the closing sentence of a book without the disruption of page headers, page footers, and this kind of stuff, which would actually disturb the overall flow of the text as you read it in the book. Again, this is then only once you have this, or hand in the hand with this, we always need to be engaged in some sort of text cleaning and normalization. This is unavoidable. Then usually what follows is some sort of morphological analysis. That means that we adopt some automatic tools for detecting what are the dictionary-like forms of words, the so-called lemmata. We are also interested in what part of speeches are used within a text, like what are nouns, what are verbs, what are adjectives. And there are now computational pipelines, automatic pipelines, which do this for Latin as well. And only after that, once you have a morphologically analyzed clean text, machine-readable clean text, we can proceed with the stuff I will actually introduce here, right? That's the thing. Okay, so if there would be a question, can we do this with your text or with a specific corpus you have in mind? Yes, as far as we are able to get to this phase, right? Since that moment on, we can basically apply it on any sort of text. So that's what we can describe as the phase of text modeling, producing word embeddings models or whatever. And once we have some sort of models, we can proceed with some analysis and only finally some maybe hopefully cool visualization things. So what I would like to from you to keep in mind is that there is a big difference between just digitization something or making something available digital and making it machine readable, right? Like for most of the stuff I'm interested in, I actually need not only digitized stuff, but also something what is machine readable. There is no single tool to cover all these phases of preparing the data and proceeding with the analysis. However, if you start to use open source programming languages such as Python, this allows you to build a sort of a scalable workflow, which will also work with thousands of works in one step and integrate most of them. Even OCR can be now done in Python, but maybe it's not that much user friendly for a humanities scholar. Another keyword I use here already several times, and which is actually crucial for the tool I will presenting here, and which is also evident, as is also evident from the title of my presentation, is the term vector. So maybe similar to me, you can relate to your high school education that you heard something about this term in your math classes. And not that much since that phase on. That was my case. I only started to dig again into what a vector is during my PhD studies. And actually, vector is technically speaking is a list of real numbers. Each of these numbers is a component of the vector, and a vector is a sort of carrier which express what is needed to carry the point A to the point B in a space, in a 2D space, 1D space, not that much one dimensional space, but mainly 2D space, 3D space, but also in a multidimensional space, right? Which is difficult for us to imagine what is a multidimensional space, but mathematically speaking, it is possible to operate with it mathematically. And so in a 2D space or 3D space, I think it's very intuitive once we look at this definition here. In 3D, a vector consists of X, Y, and Z components, right? You can imagine them as the values for on specific axis, and which are telling you how far to move along each axis, that's the direction of ultimate direction of the vector is the combination of these three components, which direct somewhere as an arrow directing somewhere. And there is a whole field of linear algebra, which is actually the field which is absolutely crucial for basically everything we do on computers today, from imaging from what we see on the screen now, and which is also critical for what any sort of text analysis I will speak here about, because it's the field which offers the right mathematical tools to work with vectors, to combine them into matrices or tensors, to compare them between each other. That's because that's the critical aspect here, that we can compare different vectors within the same space, or we can also transform them in different ways, right? Vectors are often compared numerically, and one standard method which is used and which we also apply a lot in our tool, which I will introduce later, is also so-called Cosine similarity, which might be criticized by mathematicians as not being that suitable, but it has very good and solid empirical results on textual data. The vectors we talk about are often multidimensional. Usually they have hundreds of dimensions, but once we want to somehow inspect them visually, we usually reproject them into a lower dimensionality, right? Like you have something in 3D and you can project it into 2D. And we do something similar when we have a 100 dimensional vector, a word vector, and we want to inspect it visually, that we project it into a 3D or 2D. That's a common thing, and there are standardized algorithms for that, which we also use in our tools. Okay, so vectors, and what about word as vectors? This is again something very general, but important to have in mind, that once we numerically represent something as an ordered list of numbers, like you can take a person and represent it as by its weight, by its height, by its age, you can treat it basically, these values, these numbers, as components of a vector, right? Like a row in a data table can be treated as a vector. Therefore, we can have vectors of persons, vectors of images. There is another common field where we used a lot of vector representation is image processing, basically. We can represent words as vectors, and we can also represent whole documents or books as vectors, or sentences as vectors, as is common nowadays. But how you can obtain this multidimensional word vectors in our case, because we are interested in words and in language data, how they can be obtained? Usually there are two basic ways. We either obtain them from what is called word co-occurrence statistics. That means that we have a corpus and we analyze in what context specific words appear. We produce some sort of metrics. Yeah, we are already in linear algebra, and we are able to produce a table like this one, for which words tend to co-appear together in the same documents. Like here, we have two sentences. There is a bird sitting on a wall. The cat is sitting on the fence. And you can say, okay, bird and is appearing in the first sentence together with the other words within this sentence, and the same for the second sentence. Then you can easily transform this matrix and you get the so-called word co-occurrence matrix, and you basically have a vector representation of a word. And if you do this with a large amount of data, large amount of words, and a large amount of sentences and documents, you basically get something very similar to what we will discuss here. But when I say large amount, it about at least, you need at least 10,000 sentences, or ideally at least like 1 million words to get this, and to produce some meaningful information about language as such, not only about the specific documents you have at hand. This is a traditional way how to obtain word vectors. This is nothing new. The concepts behind that go back to the 50s, basically, to some linguistic trends in the 50s, inspired by the work of Ludwig Wittgenstein. But then we have an advent of neural network-based approaches, which go back to around 2010, 2013, especially with the advent of the so-called Vojtech algorithm in 2013. And that is that instead of calculating big matrices of co-occurrences of words, you can basically train a machine learning model, an algorithm, to automatically predict a word missing in a sentence. Like if you have a sentence like on the right, she is a dancer, there are some words which have relatively high probability to appear in this sentence, like great or bad or poor or whatever, which can be compared against some other words which have very low probability to appear in a sentence like this. And again, if you have a large corpus of texts, and if you design a machine learning algorithm model to be trained on this data, and you always just hide one word from a sentence and push the model to predict what would be the missing word, there the models can actually learn what is the highest probable word appearing in any sentence, right? And this is actually that's the general machinery which we see also behind all the large language models nowadays. But again, this is something that has a bigger history going back to 2013, where the first algorithm starts to produce very nice results. But there are some important steps in between. Yeah, I mentioned that this has somehow relatively rich historical roots. One of the famous paper is the paper by Zach Harris from 1954 on distributional structure of language, where he actually speculates that if you have a large corpus of texts and you will be able to measure the context in which a word appear, and you would do it for multiple words, you would be able to detect what are actually synonyms. That synonyms are words which numerically appear, which tend to appear in the same context, right? That is in the basis of their replaceability. That was the idea at this point, but at this point there was no computational power to actually bring this to work. And there also was not enough digitized data. Yeah, that was the second limitation. But conceptually, the idea was already there. The whole idea behind what we are doing here and what I will present in our in the tool is nothing new. It can be traced back to this already to this publication and several other papers from this period. The new thing is that nowadays it's much easier because we have the digitized text, which are OCR recognized and which are machine readable, which can be used for making this analysis. There is one important distinction in computer science and linguistics that some scholars speak about this so-called first order co-occurrence of words and second order co-occurrence of words. Right? First order co-occurrence is something what is quite intuitive, that you have two words and they often tend to appear together within a sentence or within a phrase. But there is this second order co-occurrence, and this is the thing we are interested in here. It's sometimes called paradigmatic association. This is that the terms, the two words, don't necessarily appear very often together, but they tend to appear with similar words. Right? Like eye doctor and oculist are two words which probably there are not that many sentences in which they would appear together. But there is actually a lot of other words which tend to appear together with these both words, so to say. So it is something what is statistically measurable. So when we speak about distribution semantics and word vector models, we are actually interested in this second type of co-occurrence, this second order co-occurrence. This is something what often confuses people, so I put a lot of emphasis on that here. Yeah, if you want some reading on that subject, I would highly recommend the papers by Alessandro Lenzi and his PhD students over the years. He has some very nice overview articles even on the history and also on comparison of different architectures. There is also a book by him and one other author, which is quite recent. I would like to put it here at some point, but I think this paper, distribution models of word meaning, is enough to get some basis. And it's also interesting to realize that these word vectors models of meaning have some solid grounding in cognitive science and cognitive science of language and meaning. So here is some overview of how time goes. That, as I mentioned, the history goes back to the 80s, maybe 90s in this on this particular slide. And here, this gives you an overview of some basic algorithms as they were introduced over time. And there is one important breaking point at some historical moment I will introduce shortly. But here, what the tool we developed is based on this so-called fast text algorithm, which is basically just a variant of the word-to-vec algorithm. So it goes back like 10 years back. So when I speak to people from computer science, natural language processing, they perceive our work as very outdated already because a lot of stuff happened since in the field. The type of embeddings, there are different kinds of embeddings, and we have made this make this distinction because on one hand it shows some limitations of our approach, but at the other hand it also shows and explains why we chose the specific algorithm for our tool we chose. There are so-called type-based embeddings. In linguistic, type is a dictionary entry, basically, like the word as it appear in the dictionary. So not necessary, maybe that's not exact definition, but type in the type-based is like a dictionary entry, I would say. Each word type from a predefined vocabulary is represented by one multidimensional vector. We have a model, and which in the model there are individual words from a vocabulary, and each is assigned a specific vector based on the co-occurrence statistics I just spoke about, right? They are so either from word co-occurrence patterns, that's the first case, or probabilistically from neural networks. That was the two types I already introduced. And in this kind of models, words which have similar with similar vectors usually also tend to have similar meaning. That's the whole idea. That's the whole motivation why we build this kind of models, because they allow us to detect words which are used in a synonymic manner, or at least to identify terms which are used in a semantically related way. Here are some examples on super small corpora. Usually the corpora to produce this kind of models have to be bigger. But then there are token-based or contextual embeddings, and I will have to run through this only on this slide. Maybe if we have time in the discussion, I can show you something along these lines, because this is something we work on too. This is the more recent development, or this somehow reflect the more recent development, the advance of the so-called transformer-based neural network architecture, which is actually the thing which is behind the so-called the nowadays large language models, right? And in this case, actually, you don't have just a vector for each vocabulary instance, but you have actually a vector representation for each instance of a word within a text. So you have a sentence, and you encode the sentence by this kind of model, and for each instance of each word within the sentence, you will get a specific vector. And if you have a difference, another sentence, and the term appear again, it might well happen that the vector representation will be slightly different in this case, because it will be informed by the actual context in which the word appeared there in the second sentence. And this methodology actually allows you to address polysemy, which is something what you cannot address that easily with the type-based vectors, which are the subject here. But as I promised, this will be, I have to sketch this only very quickly. So in short, type-based word vectors models, one fixed vector for each vocabulary item. This is a historical older methodology. It is good at capturing semantic relatedness or synonymity between words, but it somehow struggles with polysemy. In some cases, it's useful the way how it struggles, as I will try to demonstrate to you in our examples. But still, if you have a polysemous word, you have just a single vector for it, which somehow collapse all the different senses into one vector representation, what might be a sub-ideal in some cases. And the neural-based variants of these usually require more training data, but it is still something you can do very easily with historical data for Latin, for historical alchemical prints, for instance. Once you have dozens of thousands of sentences of computational digitized data, machine-readable data, you can train these models from scratch, basically, right? In case of token-based contextual word embeddings, the situation is more complicated, because these actually have to be somehow connected with bigger pre-trained models, which to be properly trained require at least 1 billion words, which is basically more than we have for the whole Latin from antiquity to early modern time. So how to train this kind of models is some sort of challenge, or how to use them in our domains. Here's an example how a vector looks like. So here you see just first 6 dimensions of a vector aner in a corpus of ancient Greek text. Next to it, there is also a vector for theos, for God, in a corpus in the same corpus. And the whole point is that what you can do now, once you have these vectors, you can compare these 2 rows against each other. You can measure their correlation or cosine similarity specifically. And if there is a high value, you can say they tend to be somehow semantically related in the corpus. If there is lower correlation or lower cosine similarity, they tend to be more distant from each other in terms of meaning or semantic relatedness. Right, and then you can project this into this, what is a cosine similarity matrix, where you can actually spot these values. So there is this is cosine similarity of each vector against each other vector in the vocabulary, and so this is something what we also have behind our app, but where is it not that clearly visible. And if you train models for different corpora, and you do it in a solid way, you can also measure the change of meaning or development of meaning of words over time, so-called semantic change. You can detect semantic change and its trends. You can detect which word goes to the highest extent of semantic change, which word tends to be relatively stable, and this kind of stuff. Here's just one relatively famous article on that, which is still older than the newest development with transformers and token-based embeddings. But this is basically the methodology we are using in our tool as well. And now, more specifically about what's in our tool, which we called IWEMs, Interactive Word Embeddings for Early Modern Science. So we create not only one model, but we created like, the numbering differs, like 15 different models, so to say, or at least we trained 13, but we collected 15 in total, because we also bring there some models which were trained by another team, so to say. So what data we cover? For what kind of corpora we offer these distributional semantics models? Mainly, one important source is the corpus called Noschemus, which is a corpus covering 1,000 early modern Latin scientific literature from early modern period, and the different texts in this corpus are classified as being from specific disciplines, or associated with specific disciplines. This naming conventions of the discipline is problematic, but we take it as it is in the corpus. And some of the categories are highly overlapping, and a work can be actually classified as falling into multiple categories. This is often the case. And then you can see MLab there, the corpus which was presented last time. Here in the version which is now available online, MLab has only 3.5 million tokens, but our current version we will publish soon has already like 6 million tokens or 6.5 million tokens. It's much bigger because there are some longer texts in the later period. So this will still change a little bit in the years. And here you see the distribution of sizes of subcorpora from different disciplines and also from different periods. And basically for each of these subcorpora, we trained its own model, its own distributional semantic model. So with that, you can basically inspect what's the meaning, or what are the most semantically related terms to a specific term within a specific subcorpus from Noschemus, from MLab, from specific part of Noschemus, and also in comparison to two additional corpora we add here, which is Lasla, which is a representative sample of classical Latin literature, and Opera Maiora by Thomas Aquinas, which somehow gives you hints of what was the case, how specific words were used in the High Middle Ages. Yeah, here is the whole pipeline of what we did within the Tome project, how we integrate different corpora, and basically what's relevant for us here is this in the red square. We have a specific GitHub repository where we have code for cleaning, further cleaning and enriching the textual data from Noschemus. We have our own repo where we further curate the data from MLab, from the early modern alchemical prints corpus. Then on that basis, we train our models, which is also one GitHub repository, and then you have the app. So basically, if you would like to use this for your own research, you can take any of these sources and develop it for your own purposes, either the textual data on input or the models as we have them, or the algorithms we used, whatever. Everything is available. Here's some slide about how Noschemus look like on their website. So you can basically go through each work there, but we work with them using a different workflow. We don't use the website because the website allows you to do some specific stuff, but that's not suitable for the kind of computational text analysis we are interested in. So we basically had to download all of the texts, or we obtained them directly from the developers of this database. Yeah, here is some distribution of works, temporal distribution of works, and disciplinary distribution of works in Noschemus. And here is as another repository of our MLab corpus. This is still the old version, or old version from May. We will now soon publish the newer version once I figure out how to properly encode all the text and all the paratext and symbols. But it's already here. You can also download it and start to work with the texts if you want to work with them in a computational manner. There is also the graphical user interface Joe presented last week, which is also under development now. And so what we do with all these texts, we have to preprocess them to first, before we are able to train the models, we still have to engage in a lot of preprocessing, mainly morphological analysis, because we don't want to treat each declination of a noun separately. We want to be all these instances to be represented by one entry, to have one vector representation for all of them, or all forms of a verb in which it can appear, we have to represent by one word. So therefore we need the actual dictionary-like entries of these words, and not the form in which the words appear in the main text. So to achieve that, we use some automatic tools. Again, these are nowadays mainly neural network based, which give us at the end each word as annotated as whether it's a noun, whether it's a verb, and also accompanied by a lemma, by a dictionary-like form. So basically, this is one working format of the data we work with. There is a Latin sentence, and for each sentence, we trace the source ID of the source Noschemus document. We also assign each sentence ID, and then we have the word as it appears in the text. Then we have the word as lemmatized. Then we have the part of speech, adjective or adjective, and then we also have the position of the word within the specific sentence. These are the two numbers on the right. We have some additional data nowadays, but this is the critical. You can spot here some issues. The issues can be also related to the problematic OCR, but often these are also problems with the pipeline, automatically morphological analyzing pipeline itself, which hasn't been trained properly for early modern text especially. And then for each of our subcorpora, for which we have the models, we also somehow capture the frequencies of different words, because this somehow allows us to produce a right vocabulary of terms which we can trace over all these subcorpora. So here you can see each row is a specific word in the vocabulary, and each column you see its frequency in the specific subcorpus we work with. This is something we had to do because this then allowed us to produce vector representation only for certain words, because to produce a proper vector representation you need a word which appears with at least some frequency. If a word appears too rarely in a text, the model doesn't have enough training data to properly learn its co-occurrence patterns, and therefore to learn to predict where it should appear or when not. So again, a summary, based on the vectors are based on MLab and Noscemus and the additional two corpora, but in that case we haven't trained the models on our own, we just inherited them from another project. We use this so-called fast text algorithm, which is this prediction-based, type-based word vector model. And we use the same algorithm, the same parameterization of the model for the training as was used in this publication here, which is the publication where the two other models we involve are introduced. This is a technical stuff. We don't have to be concerned by that much. But also, in addition to the models themselves, we also have to make these reprojections of the raw vectors into 3D or 2D representations. What is actually what you can see most directly in the app, right? But this is just a reprojection of the original data, the original vectors, as we use them for the analysis or for the quantitative part behind the visualization is based on this original 100-dimensional vectors. So now to the tool itself. So what it offers. There is an about section where you can check basically the basic stuff I just try to explain is explained here, also including the methodology of how we chose the words for which we offer the vector representation. And there is nowadays also the publication, the paper, which you can find in the Journal of Humanities Data. It was published quite recently, where we offer a more detailed documentation of the whole pipeline and the rationale behind. And when you go to this part, to the visualization app, there are actually three different parts, which are actually very closely related. Maybe, hopefully, the most interesting part is this one. Right here, you can just select a specific subcorpus for which you want to get the models. Like I can take MLab, and I can choose a specific word for which I want to inspect. Maybe Scientia might be good cases here. And as far as the word is in the vocabulary, I get this, and at first it's not that nicely visible. You have to get used to it a little bit to get the most of it. This is a three-dimensional representation of the vectors, where the positions you see here are some sort of reprojections of the original vectors from the original space, and something what is close to each other means that the vectors are similar, right? If the vectors are similar, the words here will be close to each other, and that means that there is probably some sort of semantic relatedness. If there are two synonyms, they should be just upon each other if there is enough training data. And it might be a bit confusing if you look at it this way, but you can rotate this and you can zoom on. And once you zoom and rotate it, I still think that you can get more insights out of it than just by looking at the image in a static way. So that's the reason why we implemented it in this way, that once you rotate, you can actually see, okay, maybe it first appeared that the term is quite close, but then you rotate it and you realize actually that was just because of the projection, right? But still, consistently, you see that some terms are quite far away, and the terms which are quite far away from scientia, this does not mean that they would not be related to scientia. That means that these terms are related to scientia here, but also they are related to a number of other terms which are not visualized here, but which somehow drag them to the actual location here. This is something what is a design decision we had to make to how to properly, what to visualize in what way. And there is like 5,000 words in each model. If we plot here all of them, nothing would be visible. So we basically visualize only 20 most related terms, with 20 terms with the highest similarity score to the target vector here. And you can even increase the number up to 100, and once you have 100, you see that actually it might get a bit complicated to navigate in it, but still, if you play with it for some time, you can get used to it, right? Once we speak about alchemy, let's check out something more interesting. Hopefully, like here, you can, for instance, spot how aqua is represented and what are some similar terms, or which terms are somehow treated as being related. And yeah, there are some mistakes, obviously, but in general, I think it somehow works. This is something what is the interactive element, but it is not good for if you want to print something, right? If you want to, or if you want to take it into a paper, then you are in a trouble. An option would be to have there a static 2D image as well. Maybe we will add it at some point, because that's something what we also often use in our publications. Here you can actually see a table which shows you what are the terms, and here on the right side you see there is a similarity score. That's actually the number which is which should be taken more seriously than the image itself, because this somehow says you what the numerical cosine similarity between the two vectors. But of course, yeah, this is something what you would need some mathematical training to understand properly what it means in terms of semantic. Another figure here is so-called of confusion matrix. And here you can, the color of the specific patch corresponds to the extent of the or the value of the cosine similarity between specific two vectors. So here, for instance, you see that maybe we can choose a different term to find some nice example. Like if I take Mercurius, for instance, and only 10 words closely related to it, I can see that, okay, amalgamo is closely related to amalgama. So this, and yeah, it's a question whether to treat these two separately, but actually that's how the model works, that it actually detects if something is interexchangeable between each other. That's what you should see here, right? And so far we looked only at NLAB, but you can also look at other subcorpus and see the differences. If we have Mercurius, an interesting case, if we move into astronomy, astrology, cosmography, where you actually see how the early modern astronomers and cosmographers treated Mercurius, how they use this term in that context, right? And you see a completely different context here. And even maybe a different context would be if you would look into other disciplines or other corpora. For instance, in that case, if you look into meteorology or earth sciences, or if you look into Laszlo, which are the classical authors, right? Again, a different context, which in that case will be If we take more nearest neighbors here, you would see here some mythological figures morely widespread in the lemata. But that's still not everything. Other aspect of that, basically, I don't think that the app like this should be end product. Actually, maybe the models as such are more valuable on their own. So if you have some basic skills with using Python, you can easily download the models and run them on your own and develop your own figures based on them, right? So because this is meant for some sort of exploration, and this is hard to get out of it something publication ready, I would say. But another functionality is this, which is a tool which allows you to do some cross-corpora comparisons. So if you take Mercurius again, the figure here shows you where between which corpora the term Mercurius is used similarly versus differently, right? The scale to which the usage, the vector within one is similar to the vector of the same term in the other. So for instance, here you see that actually, yeah, everything is quite far away from Laszlo, because Laszlo is the classical Latin corpus and term Mercurius is used there completely differently. It is used similarly to itself. That's why here on the diagonal you have yellow. The yellow means that it's one, because yeah, the corpus is identical to each other, or the meaning of the term it is identical to its meaning in itself. But then you see that actually the colors here tend to be relatively dark on this scale. An interesting case for you might be, again, that once we look into the row corresponding to MLAP, like the early modern Latin chemical prints, we will see that, okay, which part of Noscemus is most similar to it in terms of how Mercurius is used there. And you see that, okay, it seems that in the earlier period, in the second half of the 16th century, there is a bit slightly more bright color, but obviously the brightest color is here, which is Noscemus, the works in Noscemus classified as falling into the category of alchemy or chemistry, right? So that's obviously that is nothing what should surprise you, but it is something what should demonstrate that the models somehow work, right? If that's always a tricky part, how to navigate between these two extremes. That if I show you something extremely surprising, then I could be easily accused of that. How do I know that it's valid? Right? So therefore I would first, and that's my task here, to show you something where you can see that this approach to the topic is valid and valuable, but it's upon someone else to find actually what new can be found with a tool like this. So now just shortly back here. Here is basically what I showed you. We also have in the supplementary to the paper, you can also produce a different hundreds of different figures with this kind of data. Like here we manually annotated different words as material substances versus astronomical bodies, and then we checked Mercurius against these in the corpora. But we also have experiments with contextual embeddings, where you can measure how sense of different words change over time. This is the different kind of methodology, but for us, a natural continuation of this development. And yeah, finally, I like this figure because for me, and I think that maybe for you, I'm thinking about academic cooperation as a sort of adventure which can have a different form. I can either be a solo performer, like most humanities scholars often tend to be, like writing my own monographs and then presenting them to the audience somehow. In some academic disciplines, it's quite common to arrange academic cooperation, like in an orchestra, where you have a conductor, which is actually giving tasks to individual orchestra members. This is the way how it often works in the context of computer science or engineering disciplines in general, where it's very where the approach to research is very often very top-down oriented or top-down based, with professors assigning tasks to their PhD students on a very strict basis. But then there is a model of a jazz combo, of a jazz band, where everyone basically gets a floor to improvise, to bring a solo, perform a solo, to be involved in that. And in the meantime, the task is to support the rest of the band, but it somehow shifts from one moment to another. And this is actually how I see how a collaboration between humanities scholars and computational experts can and should look like. Right, like that, and I'm putting this here that in case you would somehow like to use this kind of tools, but you don't have the right computational skills, that doesn't mean that you would have to go and study Python on your own. I still think that the more viable approach would be to team with someone who already knows this kind of skills, and to find a setting in which each of you can find a space to realize your own research needs in a team with someone. And I think that this is still something what we in the humanities need to learn more to profit out of this kind of collaborations. Thank you for your attention, and hopefully we still have some short time to discuss all this stuff.
Well, thank you, Wojtek. I don't think we actually have any more time.
Oh, sorry.
But I mean, yeah, if there are any pressing questions, I guess I could take them. But I guess there's a question from Sarah. Sarah Lang. She's asking, did you create some visualizations, analysis about interesting words from their frequencies in specific corpora, where there are interesting learnings about certain words?
Were there interesting learnings about certain words? Yeah. Definitely there were some lessons, but to be honest, I was too much on the side of taking care of implementing all this code and making it running, that in this particular case I didn't care that much. No, I care about the potential and the contribution, but I was not that much involved in actual interpretation of that. But there will be an issue of Czech Philosophical Journal which will come out soon, and there is a paper on, for instance, on the analysis of harmonia using these methods, or at least an appendix on how this tool revealed some interesting shifts in this term. And that's now we are also planning to do something to go deeper into Mercurius and to elaborate this into an actual independent paper. Right, that's one of our plans with Cho and Petr Pavlas to go deeper into specific terms and maybe combine the method we used here with the contextual embedding methods. If the question is specifically about frequencies, sometimes you might be surprised to see that there is a certain term you just realize that, okay, it's completely disappeared at some point, or that it is just a term which starts to appear only in a specific time. Sorry, I don't have any specific example from this particular work here. but it was, to be honest, for me,
Shiraz says no worries
yeah,
about that.
to be honest, to my problem with working on that was that uh, I dreamed about doing something I haven't done in the past, and this is actually this kind of models is something what I did in the past with the Greek texts, and I have publications out on this same methods, right? So for me, I was more looking forward into these other methods, like the contextual embeddings and their potential, rather than exploring deeply this kind of tools. They were more like a byproduct and something what is still could be useful to many other people, I think, but more than something I would myself like to dig into, and based a lot of stuff on that in my own research.
Mhm. Well, thank you. Yes, so it's you have a lot of messages of appreciation in the
Yeah.
chat. People are very interested in
Mm,
3D
mm.
representations and that of words. You know, it's I mean, it's not very common, of course, to see that kind of thing, and it's very interesting. Um, but unfortunately, I I do have to close because
Okay.
it's we're past 1 hour and something. So I want to thank everyone for participating. I mean, to thank you, Wojtek, for explaining so well all these aspects of word embeddings that people can see again and understand. And I encourage everyone to try the tool, just to experiment with it and see what can, with different terms that they're interested in. Of course, they have to be in Latin, but you can check how relevant you find it. Any kind of feedback, of course, we're looking
Exactly.
forward to it. And otherwise, yeah, this is pretty much the end of our Turba for this year. We'll be back at the beginning of next year. I will circulate the program. Probably more like, springtime. So, but yeah, I want to wish everyone happy Christmas, happy New Year. Anything that people celebrate. It's a good time of year. Don't get cold, or stay indoors if you're in a colder place. And again, thank you, Wojtek. Thank everyone, and I'll see you next time. Yeah, thank you.